Hello, Math 126 students. I promised several of you, and you expressed interest in a little discussion of Taylor series applications. I know that when you're first doing Taylor series and error bound, it's easy to go, why would anyone care about this? Very common sentiment, especially when you're trying to figure out an error bound that you don't understand. This course isn't really about the applications. This is us trying to give you the basic tools. When you go to other courses, you'll know what they're talking about. Mostly this course was about finding these four things: the Taylor series for e to the x, sine, and cosine. Now it's kind of small to see, but I just wanted to put it there to remind you. So watch other videos for how I did all that, how we manipulate. That's what you need to know. You don't need to know this stuff, but like I said, many of you expressed interest when I mentioned this. I've never done this before. I'm not going to claim to be an expert on all the applications of Taylor series, but I personally think they're very interesting, and I just am going to mention a few that I happen to know. So apologies, if you ask your engineer friends, they probably know some better applications than I do, and they will definitely tell you. I have students that went on to engineering, and they're like, yep, I did use Taylor series a lot. So I just sort of randomly kind of thought of what I could and collected my thoughts a little bit, and this is just going to be more of a little presentation. Okay, so I kind of just thought in my mind, which were some of the big applications. So to me, the biggest one is this is just another very powerful option to describe and analyze functions. So that in itself should make it valuable, because it's something we can do for any function. We can base it almost anywhere. It becomes a very powerful analysis tool to add to your toolbox. In particular in this class, we saw that it can do integrals. We haven't seen this, but it can solve differential equations. If you took Math 125 here, you already talked about separable differential equations, which is really limited. This is a method that could solve any differential equation if the numbers are nice enough, but it can solve more than just separable. But there are some challenges that will come into play. Not everything's easy to solve, but it's a general approach. It's a way we can approximate in a very precise way. So unlike a calculator just might give us a number, this will give us a formula that will give us accuracy to as many digits as we want. So it's a little different, better than a calculator in some ways, depending on what we're trying to do. It often gives a simpler, and I'm going to give an example of each of these, a simpler but more accurate approximation of complicated expressions. That's really important in physics and engineering. We have a really complicated expression. We need a simpler form. It proves something called Euler's formula, which is extremely valuable in complex analysis. Some argue that this is one of the most important mathematical formulas that exists, and so it's nice that this gives us a way to prove it. It evaluates sums. That's kind of my own interest. I'll just mention that in a second, which may not be you may not call that an application, but I think it's cool. It proves identities, many identities. It can be used to prove things about numbers and sequences in very powerful ways. That's kind of the course where I got interested in. I took a course in something. The course was called Generating Functionology, and how to use Taylor series is what are called generating functions. So I'm just going to give you a little survey of each of these. And I prepared a few things. I'm going to show you a few things. I'm not going to work through them because I just think it takes too long. I still don't know how this is going to work. So I'm just going to do it more as a survey. It's not perfectly prepared. I just worked on it today in between doing other things and just thought I would see how this goes. Okay, so let's talk about some of those as we go through. So, just quickly, I think I'll say first solving differential equations. So a differential equation is any equation with a derivative. So we know how to solve that. We integrate, but there's another way to solve it. If someone told you the solution to this is a polynomial, you could solve it by kind of guess and comparison as follows. You could take the derivative of that and say, I don't know what this number is. I don't know what this number is. I don't know what this number is, but I'm going to construct a polynomial that's a solution. That's another approach to solving for functions. Now functions can be thought of as polynomials, possibly extended out. So you could say, I'm just going to start finding the coefficients. That's another approach that solves lots of problems. You just then differentiate it and say, well, that's going to be a 0. That's going to be b. That's going to be 2c. And then you do something we call comparing coefficients. We do a little bit of that in Math 125. It's really valuable here. So you say in order for this to work, the constants have to be the same. So b has to be 7. In order for this to work, the coefficient in front of x has to be the same. So you get 2c has to be 6, so c has to be 3. You get 7. You might try to integrate and see that you get the same thing. You would have this a, which is the constant of integration. And there's no way to know what that is unless someone gives you an initial condition. Okay, so that's kind of a fun one. Another way to think about integration is to try to find the polynomial that works there. Now, what does that look like in a more general setting? What if the polynomial doesn't stop? So let's say we're trying to solve this. If I was doing this in class, I would separate and integrate. That's what you learned in Math 125. So here's another approach, and this approach works for some things that aren't separable. The approach is to say, I don't know what the function is. I'm just going to write a0, a1x, a2x squared, a3x to the cube. I'm going to write the Taylor series for the answer and say, I don't know what the coefficients are, and now I'm going to solve for them. This is really a powerful method, this idea of you're trying to approximate something but you don't know what the terms are, so just think of your function this way. If you differentiate this, even though I don't know what it is, that'll be 0. That'll be a1. That'll be 2a2. Again, you don't have to, this is not required for this course. And then you substitute those in. Now, I put an initial condition there to make it a little easier, so that must be 1. So they told me that's 1. And then I'm going to take the derivative and put it here. I'm going to take the function and put it here. And then I'm going to equate them. And that actually works. It works to solve. What do I mean by equate them? I want this to be that. Those are the constants. So a1 has to be a0, and we just said that's 1. So I started to build this up. This has to be 1. This has to be 1. So you can actually build a function the same way we built Taylor polynomials from a known function. You can build Taylor polynomials from conditions on an unknown function in sort of the same way. So let's keep going. This means that a2, this is really dear to my heart because I was taking a differential equations course and I got really stuck on a certain problem in grad school and I couldn't quite remember how to solve it. So I did this and I got the right answer. It wasn't the way that was intended to solve it, but I always think, oh, that saved me in that class. That's got to be 1/2. Okay, let's keep going. Now I need 3a3 to be equal to a2. And a2 was 1/2, so if I divide by 3, that means a3 is 1/3 times 1/2. That's kind of interesting because that's 1/3 factorial. The next one's going to be 1/3 factorial. And then I'm going to get 4a4 is equal to a3, which is 1/3 factorial. That means a4 is 1/4 factorial. That's really interesting. The function I'm getting is 1 plus x plus 1/2 factorial x squared plus 1/3 factorial x to the third plus 1/4 factorial x to the fourth. And because you took my class, you know that that's e to the x. Now again, that's not the way I would solve that problem, but it's kind of cool to see that it works there and gives you the same answer. If you change this slightly and say plus x or something, it's not separable anymore. This technique would still work. You just would have another plus x here. And so you'd have to say this is equal to this plus 1. Very powerful method. Mostly I just want to show that for the idea. Not that you're going to do that every day. In Math 307, we don't teach that method. We wait for a higher level class. So you have a little leg up, an idea. Don't tell that instructor. I don't want to get in trouble. Okay, so that was just solving differential equations. Hope that was kind of interesting. I just really like the idea of showing you that we don't know the function, so we just write it as an unknown Taylor polynomial and we solve for its coefficients. That's pretty slick. Okay, something else. Let's talk about integrals just really briefly. I have a big example here of integrals. I just like to use this as an example. This is a really famous integral. This is the bell curve. And it turns out this weird number, square root of 2 pi, in order to prove this is the right number, you use polar coordinates, but I'm already going to say too much, so I don't want to get into that discussion. But this integral, the area under this from -infinity to infinity is 1. We think of that at 100%, and we call this the bell curve. This is the bell curve, and that's the right number to have there to make this come out to be 1. And you have to have a -1/2 there. So there's a big discussion about this in probability. It's good for things like if you had a bunch of students randomly guessing on a random test, you might expect that, the middle would be right here, and we call that the median. And anyways, real test scores don't usually come out like this. But there's a whole theory behind things that do where the bell curve does apply, and that's pretty useful. We call this one standard deviation. For those of you who have taken probability, you might know that that's about 68%. And then I always forget, 2 standard deviations like 95% or something. Okay, so those, we compute those probabilities by computing areas. So I'm going to compute the area of this, and that's going to be basically 1 probability. And I'm going to show, let's see, I'll switch over and just, there's from a probability website, actually this is not a probability website, I think it's Wikipedia, but I just grabbed this discussion of probability. There's that function, so I'm not lying to you. And then here's just a breakdown that 68.2%. So this is 64.1. These are not exact numbers. So you might say, how does someone approximate those? Well, they'd have to do an integral. They'd have to integrate from 0 to 1 to get that 34.1. What if we needed it to be more accurate for an application? Or what if we just want to know where they got that number? Many ways to approximate. So what I did was this. This is a function we really don't know how to integrate very well. None of our methods work very well. I've mentioned that a few times. So you have another approach, which is to turn this into a Taylor series. If you don't know how I got that, sort of review our recent lectures. I took the exponential series, which I know. I replaced x with all of this. In doing so, I got a negative 1/2 to the k, and I got x to the 2k because there was already a 2 there. That's it. And then integrating is really easy. If you want to integrate, so I'm integrating from 0 to 1 to get that area. If you want to integrate, the only thing that changes is this becomes this. I talked about that as well. And then you evaluate at 1. And you get the answer. This is the exact answer for what that 34.1 is. To any degree of accuracy you want. I don't know if that makes sense, the power of that. It's not just a calculator giving me 3 digits or 4 digits or 8 digits. This is the answer. If I'm just, as accurate as I want. In particular, whenever there's factorials on the bottom, it's going to converge really fast, we say. So you're not going to have to go very far. In fact, I did this just out to the first digit, and I got 0.3324. I went up to the second, I got 0.342. Remember, it was 0.341. I went here, and I got this. This one's accurate all the way out here. So this really is the value for sort of 1 standard deviation in a pretty accurate way. In practice, let's say you wanted to make a computer that gave that number or run a program. I just tried to think of the simplest thing I could do. I made an Excel spreadsheet, and I just plugged that formula in, and there's our numbers, there's our approximations. And you can see this. Okay, so you can see those approximations. In reality, we don't really do error bounds, we just compare. So if I was trying to get an accurate answer, I just would say, well, these two have the same first 2 digits, these two have the same first 3 digits, these two have the same first 4 digits, these two have the same first 6 digits. And so I basically would go until they don't change anymore. So it looks like right here I'm accurate to 14 digits. In running this program, I realized that WebAssign only uses Excel only uses pi to 14 digits. So I can't get any more digits of accuracy from Excel. I need another programming language or something to do this. But there you go. It doesn't take very long to basically get an answer that's good enough for anything we're going to do. And then if you wanted to multiply it by 2, that would be the standard deviation is 68.26. So I think that's kind of interesting. Not so much that you couldn't find that approximation somewhere else, but that this just gives you a general way to give sort of exact answers if you're willing to accept that. Okay, so there was a little bit about integrating and a little bit about generalized approximations in a precise way. Okay. Let's take another one. How's my time? Okay, good. So this is just a little survey of some things. Again, you don't have to know that. I mean, you do have to know how to go from here to here. That's a big thing we did. I'm just pulling out a few interesting things. Okay, so here's this. I'm not going to claim to be any sort of expert on physics, but if you take a physics course, you often hear people say things like, okay, Einstein had this theory that the energy was related to the speed of light, and the speed, and that is this, as the speed of an object gets closer to the speed of light, it changes the energy. I've heard of those things. Like I said, I don't claim to be an expert, but I also have heard in those courses they say, but at low speeds, it approximates the original theory, the Newtonian theory. I don't know if you've ever heard things like that. Here's a way to make that idea precise, what they mean by that. So here we have a function. Let's think of this as a function of velocity. This is just some fixed mass, and this is the velocity, and then this is the energy. And someone gives you this formula. It says, I want you to approximate what happens when the velocity is pretty small. And in fact, in advanced courses, sometimes we even use like weird symbols like this to say the velocity is much, much less than the speed of light. Okay, in other words, this term right here is really close to 0. Okay, so let's kind of think about that. But in that case, you just get 0. So what if it's not quite that close, but we want to approximate? Okay, so if v is small and close to the speed of light, you can basically, I'm going to take this function right here and I'm going to approximate it. It's the only thing that has v's in it. They are some messy derivatives, right? The derivative of this with respect to v looks like this. The second derivative is this big messy thing. But let's just write them out. And I'm going to get the Taylor, I'm going to build up the Taylor polynomial, the approximation of this thing. So if I plug in a 0 here, I get a 1 there. If I plug in a 0 here, I get a 0 here. If I plug in a 0 to this whole thing, I just get a 1 over c squared with a half there. So often that's what people do. It's very common to go to the first or second term. So then you basically can say, what do I got? Well, I can now replace this thing in the green with this. Pretty good approximation, has a very small error if v is a lot less than the speed of light. And when you replace that with this, the ones cancel because you have that. So this is the thing I just replaced. That one cancels with that one. You get this. The c squareds cancel and you get 1/2. And this is the end. Interrupting my video, small typo alert. I'm about to post this video on my YouTube channel, but I realized the students and people viewing this video there will not be able to see my warnings about a typo. This C should be a V. I just canceled wrong. Hopefully that's the only typo there, but that C should be a V. So before people comment that this is wrong here, I'm sure there's other things that are wrong, but this is one I'm aware of. All right, back to the video. Kinetic energy formula in Newtonian physics. So that's a way to make that precise. That's what they mean. So basically the Newtonian physics formula is a second order approximation of Einstein's theory, and that's why you can kind of say, okay, the theories kind of fit together. It's just this starts to not work so well when the speed of light gets higher. Okay, so there's an example of just an easy one I could pull of a messy formula where we could approximate. That's used a lot. Okay. And that's for those students that said, we have a calculator, what do we care about this for? Well, here's something that it has nothing to do with a calculator. Okay. So that's this idea. I do want to say something about Euler's formula. I'm not going to prove it because it's just too much time, but I'm just going to pull it up here. So if you're still thinking about that, you can pause on that. But I'm going to pull up something on my screen, and let's go here. So this is from my Math 307 course website. This is something I created years ago. In Math 307, we need... In Math 307, we need to use complex numbers just a tiny bit. We don't have to be an expert on them, but they are necessary in that course. And so I have this little sheet that sort of goes into more detail about what are complex numbers and how we think about points in the plane as we actually think of a complex number as this is the x-coordinate, this is the y-coordinate. But the arithmetic leads to some cool geometric ideas, like how to quickly rotate points in 2D and stuff, and how to solve equations. So I go through all that. But ultimately, the big thing is, you see that one of the most common formulas in math is this one, or one of the most famous and useful ones, is this weird expression where there's an I in the exponent of the exponential function. It's really just a fancy way to write this. It's also related to polar coordinates. This all kind of ties in together, but it has this weird I, where I squared is -1. So the reason people use this notation is because it makes sense in our Taylor series. It all matches up. And that's because of this. So here's the Taylor series for e to the z. This is from that course. So students that take that course that skip Math 126 kind of have trouble with this. We don't spend a lot of time here, but I say here's the Taylor series for this, here's the Taylor series for sine, here's the Taylor series for cosine. I basically say these are all connected in this funny way because I squared is -1, I cubed is -I to the fourth is 1, and then it repeats every 4. So there's this cool thing that when you plug bi in here, you basically get this, you get this, you get I squared. This becomes -1. And contained in there, with some cleaning up, is this, which doesn't have any i's attached to it because those have all been changed to 1s or -1s, and this, which does have i's attached to it. And that happens to be cosine, that happens to be sine. It's kind of a beautiful little piece of work about how this e to the x and the sine and the cosine series are actually connected in a way. And it gives us this shorter way to basically rotate things in 2D by multiplying by e to the b is like your angle. So that's a big, important theorem if you take complex analysis or if you leave this course. Okay, so just wanted to say that piece. So hopefully that's kind of interest. What else do we got here? Okay, so there's that little discussion about Euler's formula and complex numbers. I just wanted to mention, I don't know which of these is better to do. Let's talk about evaluating sums. I will do that next. Actually, I don't know. I think evaluating sums is kind of fun to end on because you can relate to that. So proving identities. This particular really is not something you would see till a higher level course. I just wanted to mention it because, like I said, it was what interested me in this topic. So if you're studying some sort of sequence, this is a special sequence. This sequence goes 1, 1, then you add the two previous numbers together to get the next one. This is the Fibonacci sequence. My dissertation was related. It wasn't really on Fibonacci numbers, but it was related to what we call second order recurrences. These play a big role in lots of things. Recurrences in general play a big role. Basically, I just got a list of numbers. So there's a clever idea, which is when you're analyzing a list of numbers of any sort, place them as coefficients in a Taylor series without the factorials. Just study this. We call this a generating function. And there's this book where I really became interested in Taylor series was this book called Generating Functionology. And then analyze this function and see what you can get. So it's really kind of interesting. So this one, don't take too much into this. I realized it became really complicated. But, basically you can take out those first two terms, and then you can say every term after that is based off of the previous terms, and you can do some manipulation, take some practice getting good at that. And you can see I even I was kind of messy. So I thought rather than show this, but I just thought I'd mention this, that it's actually possible to prove what the function is that goes with this. And that becomes really powerful because it gives you a way to analyze this sequence. I always feel like you get more out of this than you put in. You just lay the numbers down on the clothesline, and then all of a sudden you have this function, and you can use it to study those numbers. So it turns out you can do partial fractions and break it into two. You get these weird numbers, which if you know anything about the golden ratio, it's appearing there. And then you can split it up into two, and then you can find the Taylor series for that using our geometric series, and the Taylor series for that using our geometric. And you get this really weird thing here. And that thing must match up with these. So it's pretty slick. And you get this formula. The thing you get in this spot is this crazy formula. And that means you get this impressive. This formula doesn't help us compute. It's just really surprising that if you plug in a 2 right here, you get 2. If you plug in a 3 right here, you get 3. If you plug in a 4, you get 5. That would have been a hard formula to come up with without some other method. So that's kind of a weird way to use series to construct a function. Here I'm not taking derivatives of anything, but it's still the same idea of laying out your numbers and using this kind of the opposite way. Okay, so I threw that in at the last minute just because I thought of that. So there's proving identities, proving important formulas. So lastly, I just thought I would talk about evaluating sums. This is my own interest. I was drawn to these in grad school and as an undergrad. I thought it was pretty cool that we could figure out that 1 plus 1/5 plus 1/5 squared plus 1/5 to the cube, that always approaches something, and not only approaches something, this is the same as the 1 over 1 minus z function with a 1/5 in there. So this is 1 over 1 minus a fifth. If I multiply everything by 5, I get 5 over 4. This approaches 1.5. I find that 1.25. I find that really enthralling, that we can know what this approaches. Now, if you wrote out the first 7 terms, you would probably guess it's approaching that. But I just think it's pretty cool we get this. Now, this is my favorite. You get 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. This is e. It's e to the 1. That's when you plug a 1 into that exponential series. That's probably the best way to approximate e. You only have to go out a few terms. You could make a spreadsheet like I did in that earlier example, and you can get this accurate to lots of digits in a very short amount of time. This is the same thing. This is actually e to the 2. So e to the 2 is 1 over 0 factorial plus 2 to the 1 over 1 factorial plus 2 to the 2 over 2 factorial plus 2 to the 3. All of those things we've evaluated now. This one's cool because you can tell it's the cosine function, and they've plugged in pi. So this is actually -1. Super weird. This one is not technical. This one requires more proof. I'm not really proving it here, but this is the log function. We talked about the Taylor series for negative log of 1 minus x, how it's the sum, and sorry, I should have a 1 there, the sum from n equals 1 to infinity of x to the n over n. If you plug in a -1 here, then you get this. So this ends up being, let's see, do I have something off there? I'm a little doubtful. Yes, I think I do. Just catching myself for a second. No, that's okay. This ends up being negative log of 2. Now, you got to be a little careful here. The comment I wanted to make was this is right on the edge of Mandelbrot convergence. I never proved to you what happens on the edge. It just so happens that the negative log of 2 approaches this weird number. This one is pretty important because this one is, this is what we got. And I'm doubting myself. I just want to make sure I copy these. I'm taking most of these examples from, let me just pull this up because I'm doing it here. Now I can explain. On my website, this is something I made for my honors class. We just sort of talked about the solutions in my honors class, but this is an old worksheet I made that's just these applications. I just have done some of them, and I've added some of them. So you can find that on my website. Yeah, I guess that's what I intended. Okay, so this is that arctangent. This is another way to write it. But arctangent 1 is pi over 4. This is one of the first tools people ever use to try to approximate values of pi. It doesn't work very well. Some adjustments are needed to give you a good approximation. But that means that pi is equal to 4 times whatever this thing gives you, which if you plug in 0 gives you 1, 1/3, plus 1/5, minus 1/7. Keep going, minus 1/7. So this does not converge very fast. Meaning, if you wanted 100 digits of pi, you probably have to go way out, make a really big spreadsheet. But that's kind of the beginning of, hey, maybe we can approximate pi because it's related to these functions, which we have ways to approximate. Okay, so there's a bunch of things. Not every series is easy to compute. In fact, very famously, this series, the 1 over n squared series, 1 plus 1 over 2 squared, for a long time no one could prove this. And then Euler came along and he thought of an infinite product method along with the Taylor series method that proved that this was pi squared over 6, which is awesome. It's pretty amazing. You compute this thing out and you compute that and you realize they are the same number. Why? I don't know. It's kind of a weird thing. If you do the sum from n equals 1 to infinity of 1 over n cubed, no one has come up with a nice closed form answer for that. I wasted a lot of years as an undergrad and a grad trying to approximate this value and say, is it log of something? Does it involve a pi? Euler proved it for all the evens. He proved a formula for n squared, n to the 4th, n to the 6th. But this one, people have proved a lot about this and can approximate it really well. There's just not a nice formula that involves pi's and logs that anyone knows of. Okay, so there's a long history of infinite sums. Okay, hopefully that's of interest to you. So we did a half an hour on different applications there. And so I'll post that and see what you think. And again, none of that's required for this course, but I hope it gives you a little bit more background of why you might be interested. And I feel like I'm missing some of the biggest applications that engineers use. This is just what I know. Like I said, I think the biggest applications are really just these things. You have a simpler way to express complicated functions. So you can give a second order, something to the second power, third power approximations. And it's another just powerful way to describe functions. in this list, there's a lot more. I know that my office mate in grad school, he did something called perturbation methods, and they always were using series to try to prove that the error got smaller by looking at the second or third or fourth term of something. So I know that there's a lot of applications out there. These are just the ones I know immediately. Okay, if you find more applications or you see this appear in other courses, I'd love to hear about them. Email me in a few years and I'll add it to my list. All right, thank you.